Okay, hi. So jumping back on here, talking about orbits, stabilizers, etc. So we just proved this fundamental equation, which tells us that, or maybe equation is the wrong word, this fundamental equality that there's a bijection between the orbit of x, point x, and g quotient out by the stabilizer. So as a corollary, let's just write immediate corollary, if g is finite, then we have the equation that the size of the orbit of x is the size of g divided by the size of stab gx, right? Because if I take g and I quotient out by the stab g cosets, the stab g equivalence relation, that set has this as a size, right? So you could rewrite this, of course, as stabilizer times orbit is g. So in particular, the orbit is a set whose size, whose order divides g. And that's something that's actually very useful in formulas. So we're going to use this in group theory to study the structure of groups and group actions a bunch. Let me give some specific. So I want to. I'll follow Goodman's lead here and introduce some terminology related to this in certain specific cases. So let's do some examples of this thing. So if x is g, and g is acting on x by conjugation, then there's some special notation terminology to introduce. So the orbit of g, so I'm fixing a little element g in g, which is x in this case. So this is the set of all things that you get by conjugating little g by elements of g. So this is the set of h, g, h inverse, such that h is in g. That's supposed to be a squiggly line. And this is called the conjugacy class. So this is called the conjugacy class of g. So again, this, as I mentioned last time, this is a very important set. For instance, in linear algebra, the conjugacy class of a matrix, as we know, it has a deep significance. It's the set of all matrices which give the same linear transformation under different bases by change of basis formula, right? So this is like a classic set in linear set of matrices to consider in linear algebra. And in this case, the stabilizer is called the centralizer. So stabilizer of g, which is, this consists of the set of all h and g such that h, g, h inverse is g. Okay, so I'll just rewrite that. That's hg is gh. So it's the set of all things that commute with little g, and this is called the centralizer of little g. Okay. So I wanted to introduce that as terminology. So it's the set of all things that commute with this little g. So again, examples. So if you think about the symmetric group or the general linear group of matrices, we see that this can be lots of different things, right? So this could be, so for instance, the set of things that commute with little g. If little g is in the center of the group, that's the centralizer is the whole thing. So so I'll keep going with this kind of notation terminology. So the center of g is precisely, so this z is, comes from the German word for center, so this is g and g such that centralizer of g is all of g. So this is g and g such that gh is hg for all h and g. So this is called the center. I'll write that in English below it. Right, and it's the things, so it's, so the word, so I mean, center is maybe not the most descriptive, but it's anyway, it's just all the things that commute with every element of G. So it's a subgroup of G, which is actually an abelian group, right? So if we're thinking in terms of abelian group theory, the center of G is just the whole thing. But for a non-abelian, for instance, in matrix theory, or for the symmetric groups, or our other examples, then the center will be some subgroup. It always contains at least one element, namely the identity, but often it's larger, right? So let me give you an example of that. if G happens to be GLN of F, some field, the center of G are precisely the major C's of the form lambda, 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 lambda down the diagonal, such that lambda is an F minus 0. Right, if lambda is 0, of course 0 is not invertible, so it's not in GLN. But if lambda is in F minus 0, then this is an invertible matrix. It's lambda times the identity. And in order to be in the center of GLN, you have to actually be just a multiple of the identity. And that's not that hard to see. For instance, if you know that your matrix commutes with, it's a kind of good exercise if you've never done it. If you know that your matrix commutes with every other matrix, just start multiplying it by matrices which are zeros everywhere, but just ones in a particular spot. If you do out all those multiplications, you'll get a bunch of equalities on the matrix entries, and you'll see that they force this. You'll see that they force this. Maybe this will be a homework exercise. Actually, this is a very nice thing to do. Yeah. Okay. Now that I'm thinking about it, I'm going to make this a note to myself here. Let's make this a homework exercise for you guys. I think that's a great exercise. Okay. So that's the meaning of these things in this basic example. Okay, so we're going to talk a lot more about that in the coming couple of lectures. Before we do, we want to talk a little bit about some counting formulas. So, yeah, okay, great. So I'll give you this one classic example of n choose k. This is a very important example in combinatorics. So let's do this counting formula of n choose k, which is a great example. So the number of k element subsets in a set with n elements. So n choose k, this is n choose k. By definition, this is the number of k element subsets of our favorite set, any set with n elements, but I'll say 1 through n, right? So this is the number of ways, if you start with some collection of n objects, this is the number of ways to choose k of them, right? And this number is called a binomial coefficient. It's a very important number, right? I mean, it shows up in the binomial formula. So let me remark that. Where does this show up in math? One basic way this shows up is that if you take x plus y to the n, this is kind of an aside, you get sum I equals 0 to n, or let's say k equals 0 to n, n choose k, x to the k, y to the n minus k. So here's a parenthetical remark. If I take two variables x and y and I add them and multiply the other n times, these n choose k's are the numbers that show up in this formula. So there's some like universal integer numbers that are very important in mathematics. Okay, and there's an explicit formula for this n choose k. And how do you come up with it? So what you do is you say, okay, there's an action of the symmetric group on this set, the set of k element subsets of 1n. So you let x be the set of subsets. So it's a little abstract. It's a set of subsets of 1 through n of size k, right? So you let x be that set. And then you say that Sn, the symmetric group acts on x. So Sn acts on x by, since if sigma is in Sn, and so we have to give this thing, let's say y is in x. So now y is a subset of 1 through n, right? Then sigma of y is also in x, right? In other words, if I have a subset, now sigma is a function from 1n to itself, right? It's just a bijective map. So I can take this sigma and I can apply it to y, and I get another subset. And because sigma is a bijection, the new subset I get is the same size. So sigma is acting on x. So that's an example of group actions. Sigma is actually acting on this x, and the claim is that it acts transitively. In other words, that there's only one orbit. So in fact, all of x is the orbit. So let's say it this way. In fact, x is exactly the orbit of any given element, let's say 1 through k. So there's only one orbit of this action. And if you pick your favorite k element subset, which I'm just calling 1 through k, all of x is exactly that orbit. Okay, that's actually easy to show, right? Because if I take any k-element subset, I just send, let's call it x1 through xk, I just send 1. So if y is, okay, let's call it y1 through yk contained in 1n, you just send, you let sigma of 1 equal y1, sigma of 2 equal y2, sigma of k equal yk, right? So you just make a sigma that sends 1 to y1, 2 to y2, k to yk, and then just send the remaining elements anywhere, right? So you can always pick a sigma that takes 1 through k, this k element set, to exactly y1 through yk. So that's an easy exercise. I just basically gave you the proof. And so this set has only a single orbit, right? So we know then that the size of x, the cardinality, is exactly the cardinality of g here is Sn, divided by the cardinality of the stabilizer of 1 through k, right? The size of the orbit is the size of the group divided by the size of the stabilizer. So what's the size of this stabilizer? How do I stabilize 1 through k? What do I have to do? Well, I have to fix the set 1 through k, right? So this stabilizer is any sigma which takes 1 through k to itself. So this subgroup stab 1k, this is exactly the set of sigma such that, so I'll write it in this way, sigma 1k equals 1k. So remember, sigma is a bijection. So if it takes 1k into itself, it takes 1k onto itself. So these are finite sets. So it takes 1k to 1k, and then it takes k plus 1n to k plus 1n. All right, that was redundant, but I'm just writing it that way. Because, for reasons that you'll see in a second. So here's a k element subset, and it preserves it. Here's an n minus k element subset, and it preserves it. And sigma could be anything. If I take a bijection of 1k and a bijection of k plus 1 through n, that perfectly well defines a sigma, right? So this group is isomorphic to sk cross Sn minus k, right? The first sigma acting on 1 through k gives you an element in the k letter symmetric group, and sigma acting on these last ones, k plus 1 through n, gives you an element in the n minus k letter symmetric group, right? So the size of x is the size of Sn divided by the size of sk times the size of Sn minus k, right? The size of, this product group, its order is the product of these orders, right? And so that, of course, is n factorial over k factorial, n minus k factorial, which is probably how you're familiar with this binomial coefficient, how to actually compute it, right? So that gives you a computation of this binomial coefficient. So this is like maybe theorem 1 in algebraic combinatorics, is how do you compute this coefficient? And here's the proof using a little bit of group theory and orbits. Okay, so that's a classic. So that's a classic fact. So now I want to jump to the applications of some of these formulas to group theory. I guess I better give you Burnside's lemma first. Okay, so we've said what the size of an orbit is, and now we want to give a formula counting the number of orbits. So before we get into any real group theory, let's give the next formula. So counting orbits is the next topic. So here again, we're going to let g and x be finite, and we want to count the number of orbits. So we count the number of orbits of g on x. So that g and x are finite, and I should say that g is supposed to act on x. Okay, so we want to count the number of orbits of g on x. In other words, x breaks up into these equivalence classes, these orbits under g, and if x is finite, there's some finite number of them, and so then you can ask, okay, great, what in the world are they? Okay, so in order to state the formula, we define fixed G. So let G and G. So we want to define the set fixed G to be the set of G and G. Sorry, going the wrong way. X in X, such that Gx is X. Okay, so in the same way that we define the stabilizer, so for an element in X, we defined its stabilizer, right? Those are all the things in G that fixed it. You can also go the other way. Maybe I should have done this on the previous page, but whatever. You can define all the X in X that G happens to fix. Okay, so as before, that's in examples, that's a computable thing. Okay, and so now we're gonna make a formula for the number of orbits in terms of this data, these sets fixed G. Okay, so yeah, that's great. So now we can consider the set. So let's consider the set. So I guess it's like the whole fixed set is maybe the way to say it. So that's Goodman calls it capital F, which I guess is sort of short for fixed. And now this is the set of all G comma X, such that G times X is X. So not for a fixed little g now, but you just take all of them, and you consider the set of pairs such that the thing on the left fixes the thing on the right. Okay? So for a given little g, of course, fixed g was the set of all x's that go with it in big F. Right? So big F is the union of all the fixed g's. Right? So observation number 1, so point 1. Okay, so first of all, F is the union of all of these different sets fixed G, right? So if I look over all different G and G, and I look at all the fixed point sets, that's exactly F. So F is the union over G and G of fixed G. I should be a little bit more precise. It's the union over G and G of G cross fixed G. Right? In other words, F lives inside. So let me just be really precise about where F lives. I mean, it's hopefully clear from the notation, but let's reinforce that this lives inside G cross X. Okay, so when I take F, I say, okay, what are all the things in F? They're all these pairs. So as I run over the elements of G, what do I get? I get all the X's such that G times X is X. So those are just exactly what we defined a minute ago to be fixed G. So this is the union over G and G of G cross fixed G. This is a disjoint union because the first coordinate for different G and G, the first coordinates are different elements. So they don't intersect in the Cartesian product, right? So this is a disjoint union. So this implies that the cardinality of F is the sum of the cardinalities of fixed G for G and G, right? Because if I have a disjoint union, the size of the set is the sum of the sizes of the pieces. Okay, so that's the first thing to right. So that's the first thing to note. So that's one way to count it. And now let's think about a different way to count it. So here we counted it by looking at the union across G's. We could also count it by looking at the union across X's. So for a fixed X, I'm looking at all the G's which fix that X. In other words, I'm looking at the stabilizer. So also, second, F can be written as the union over X in X of the stabilizer of G, the stabilizer of X, excuse me, cross X. Right, so it's the same kind of decomposition, but on the other side. Right, stabilizer, this cross X is a funny thing, I'm sorry. Maybe I'll write it this way to hopefully delineate them, right? So there's a little X in X, and then I'm taking that X and I'm crossing it against the stabilizer, right? So that's all the things in G that fix it, right? So if I look at this union, I'm getting exactly this whole F. And again, it's a disjoint union because as I run over these different sets, the first coordinate they're distinct from one another. The first coordinates are distinct, so these sets don't intersect. And so this implies that the size of F is the sum over X in X of the stabilizer of X. All right, so if I add up, so if I add up the size of all the stabilizers, I'm getting the same size as I get when I added up all of these fixed points. Okay, so now we can kind of put these two formulas together and get something in terms of sizes of orbits. Okay, so let's take a look at how to do that. So if I compute these, I see that they're equal, and therefore, I mean, they're integers. So when I divide by the order of g, I get two numbers that are equal as well. All right, so there's this famous formula, which is that 1 over g times the sum over g and g of fixed g is, okay, so 1 over g times the sum x in x stab x. All right, why did I do that? Because stab x divided by g is 1 over the orbit, right? Sorry, this is supposed to be sizes, excuse me. That looked like I just am adding sets, but of course I'm adding sizes of sets. And so this is sum over x and x stabilizer of x over the size of g, and this is sum over x and x 1 over the orbit. And again, that's the size, right? Because the size of the orbit is g divided by the stabilizer of x, right? So if you want to look at the sizes of the orbits, okay, or the number of them, when you add up their reciprocals, you get this. You get this very nice. You get this very nice formula. Okay. So what is this number? X in x 1 over the size of the orbits. Looks like an odd thing to add up these reciprocals. Okay, but here's the thing: as I range over x in x, these numbers are going to be the same a bunch of times, because as I range through all the elements in a given orbit, I get the same orbit again and again, right? So this sum can also be written as the sum over O, the set of all orbits, right? So I can consider the set of, each orbit, right? So I can sum over O, and then I can add, for a given orbit, x in that orbit. Yeah, so this is supposed to be like a scripty kind of O. 1 over the size of O. Yeah, I should say O of x, but I'll just say 1 over the size of O, right? So so for any orbit, I take the sum over all x in O, 1 over the size in O. How many x in O are there? The number of elements in O. So this sum is, I have a finite set O. I sum over all of its elements. To each element, I attach 1 over the size of that set. So this is just 1. Right? So this is the sum over orbits of 1. And so this is the number of orbits. So somewhat miraculously, it's kind of cool. When you crunch this out, you actually just end up with a positive integer, which is the number of orbits. So the upshot, the theorem reads that the number of orbits is exactly 1 over g times the sum of g and g fixed g. So this turns out to be an integer. And again, that's a miracle that we'll exploit many times, right? So this looks like it shouldn't be, or it might not be, right? But it turns out that it certainly is. Okay, so we're going to talk about this in the specific case of the action of a group on itself by conjugation. Okay, so let's apply this to talking about the number of conjugacy classes. So I'll rewrite this, so corollary to this famous formula. So let G be a finite group. Let G finite. And let's consider G acting on G by conjugation. Okay, right? So the number of conjugacy classes of G. So this number is equal to, okay, so let's write the formula again. So it's 1 over G times sum over, now originally we had it as, yeah, sum over G and G fixed G. Okay, so I'll stick with that. Sum over G and G fixed G. Now, what is fixed G? Fixed G is exactly the, so in this case, the fix of G, so remember in general, the fix of G is x in x, such that G fixes x. So here G is x. So fixed G is H in G, such that GH, G inverse, is H. This is H in G, such that GH is HG. Okay. But this of course, right? So this is the set of all H in H that centralize G. Right. So in other words, it's so right. In other words, G here is stabilizing. It's exactly the set of things H, such that G is stabilizing H. Okay. So the size of this thing, so the size of fixed G in this case is what? Is the order of G divided by the centralizer, the order of the centralizer of G. Okay, so I'll pause a sec to let that sink in. Right? Because what I'm doing is I'm letting G, right? So the point is that I'm letting big G act on the fixed points here. Maybe the better way to say it is, yeah. Well, I mean, I think it's maybe I'll just let it sit as it is. Okay. Yeah. So the size of this set is exactly this. Right, this is an right. The point is that this is an orbit, right? I'm taking all H and G, and I'm considering HGH inverse, and I'm demanding that it be equal to G, right? So maybe it's worth noting that this is precisely H and G, such that HGH inverse is equal to little g. So maybe that makes it even a little clearer, right? So this set is exactly an orbit under little g by the conjugation action of big G, right? And what's the stabilizer under this orbit? It's exactly the set of things which centralize, which satisfy this equation. Okay. All right. So all right. Sorry, this is nonsense. All right, I'm not good enough at video editing to edit this out, so hopefully you guys will not be too bored watching this. Yeah, this is what I'm saying here is not quite correct. Yeah, so maybe let me. Yeah, that is definitely not the size of fixed G. I mean, this is a correct description of fixed G, but fixed G is actually just the size of fixed G. Yeah, sorry about that. So what's the size of fixed G? The size of fixed G is the size of the centralizer of G, right? So this is H and G, so this is the size of centralizer of little g. Excuse me. Yeah, okay. Kind of why I paused there. I was like, wait, this doesn't make any sense. Yeah, I apologize there. Yeah, okay. So the size of fixed G here is the size of the centralizer. Yeah, okay. Right. So okay. So that's great. So that's the size of, yeah, exactly. Okay, great. So that's the size of fixed G. So there's a couple different now equations we can wring out of this thing. Yeah. Okay. Great. Good. So right. In other words, fix of G is actually a well. Anyway. Yeah. Okay. Perfect. Yeah. Right. So if you look at this last one, you get that this is yeah, exactly. It's H and G such that HG H inverse G, and so this is exactly the centralizer of. So this is exactly the centralizer of G. Okay. So we'll return to this equation later. Yeah. Okay. So let's note that we have. A couple different equations. So we have this. So we have this equation, which is so the number of conjugacy classes. So the upshot is so there's two equations to consider. So one, the number of conjugacy classes. So how many are there? There are sum G and G, centralizer of G, G, right? So that's by taking this equation for fix G that we had a second ago and combining, we get this, right? So this is very good. Okay. And then we have a second very important equation, which is that the size of G, okay, so how do we relate the size of G? So, well, maybe I'll say the equation and then I'll justify it. Is the size of the center of G plus sum G and G, G divided by centralizer of G. Okay, so how do we get this? So this is the so the size of G is what? It's the sum over all the different orbits under the action of the size of the orbit. Right? So this is the sum over all the orbits of the size of the orbit. And what's the size of an orbit? If you're in the center, the size of an orbit is 1. If you are any other element, the size of an orbit is G divided by centralizer of G. Right? So so this is the sum over these yeah, sorry, so this is not sum over G and G, excuse me. This sum is over, so I'll do what Goodman does and just write sum over G, but it's kind of deceptive where this, all right, so to prove this, you look at the orbit decomposition, but then you have to ask, what is this sum going over? So this sum is over G in a set of distinct conjugacy classes. It's kind of surprising this equation is useful, actually, because it seems so weird, but set of distinct conjugacy classes in G minus the center. Right? It seems like I have to introduce a lot of terminology to make it make sense, which is true, right? But okay. Right, so to each orbit that has one element, orbits have one element if and only if they're in the center. So I add all those up, I get the size of the center, and then I get a bunch of things which are quotients. Okay. But still, these two things combine in interesting ways, right? So the total number of conjugacy classes is, well, the number of elements in the center plus the number of elements you're summing over here, and that has a formula here, and then this is a formula that you can get for just the total size of G. So so we'll see in the coming lectures how to play these two things off each other. All right, so yeah. All right, how long am I here? Oh yeah, 34 minutes. Okay, I'm going to stop for now, and then in the next video, which will come out, sometime in the next day or two, we'll start to apply this stuff to group theory. Oh, and I'll photocopy these notes and put them up, probably tomorrow. All right, thanks guys. Bye.